Today, we are going to discover how to select the right connection detail in fibre reinforced polymer infrastructure designs to optimise performance, constructability, and cost. You'll learn that not every connection requires the same level of reinforcement, and that reducing unnecessary crush block use where possible can lead to improved constructability, reduce installation time, and deliver cost efficiencies without compromising structural performance. Good morning and welcome to our webinar, The Right Connection, Design Part 1. I'm Georgia Lance, Marketing Officer at Wagners CFT, and I'm here with today's guest speakers, Wagners CFT Project Delivery Lead, Mitch Kelly, and Structural Engineer, Sabin Raut. Mitch is the Project Delivery Lead at Wagners CFT, bringing a strong engineering background to drive efficient and innovative project execution. Mitch combines hands-on technical knowledge with leadership skills to ensure projects are delivered on time, within scope, and to the highest standard. His proactive approach and commitment to continuous learning make him a key asset in navigating complex challenges and fostering teamwork across multidisciplinary teams. Sabin is a highly proficient structural engineer with expertise covering a broad spectrum of projects, including bridges, boardwalks, marine infrastructure, civil and electrical. He consistently delivers innovative and cost-effective engineering solutions by leveraging his extensive knowledge of FRP material properties, capacities, analysis, and design. His expertise with the latest industry software and design technologies ensures accuracy and efficiency in every project. Sabin is a passionate advocate for advanced materials, and his current focus is on exploring the feasibility of using FRP to replace traditional material in various structural applications. We're also joined by Wagners CFT General Manager, Australia and New Zealand, Ryan Leeson, who will be facilitating the Q&A session at the end of the webinar. Welcome Mitch, Sabin and Ryan. Before we get started, just a few webinar protocols. We are recording today's event and we'll make the recording public via the Wagners CFT YouTube channel. You can ask a question anytime during the webinar via the chat bubble at the top of the screen. However, we will hold your questions over to the end of the webinar for the Q&A session. And for anyone having difficulties accessing that chat facility, feel free to text me your questions to the number I've just popped in the chat now. So let's dive into today's webinar. I will hand over to Mitch.
Thanks, Georgia. That's sharing now. Good morning, everyone, and thank you for joining today's webinar, Choosing the Right Connection, Part 1, Connection Design. Today, we are focusing on a very practical question. How do you select the right connection detail for FRP structures to optimize performance, constructability, and cost? Not every connection requires the same capacity. The challenge is knowing when a crush block is genuinely required and when a bush or riveted connection will safely do the job with less installation complexity. So we'll work through some basics of the design, then look at 3 real optimization examples where connection detailing was refined to improve constructability and costs without compromising structural performance. So by the end of this session, you should be able to answer 4 practical questions. First one is, what are the 3 main types of connections used in FRP structures? Second, how do load type, direction and magnitude influence selection of these 3 connection types? Third, how do hollow profiles and fiber orientation affect performance? And finally, how do installation factors such as access, tolerance, sequencing, drilling and clashes affect the type of connection to be designed? So the aim is not to memorize a single rule. The aim is to understand the decision process so we can use the right connection type in the right place. So what are we going to cover? So we're going to start with why connections often govern FRP performance, because connections are where the load path becomes most concentrated. Then we will look at FRP material behavior and common failure modes, because FRP does not behave like steel or solid timber. From there, we will compare 3 connection options the three connection options this presentation focuses on, so crush blocks, bushers or crush tubes, and rivets. Then we will step through a practical decision framework before finishing with 3 case studies: Gingerly Beach Stairs, Lakewall Boardwalk versus Kangaroo Point Boardwalk, and Botanica Sewer Bridge. So the main thread running through all of this is that reducing unnecessary crush blocks can improve constructability, reduce installation time, and deliver huge cost efficiencies, provided the structural performance is still verified. So why do connections matter? So in any structure, the member or structural component itself can be strong, durable, and well designed, but if the connection does not transfer load correctly, the system will underperform. So for FRP, this is especially important because the material is directional and connection loads can introduce localized failure modes. So when we talk about connection design, we're really talking about facilitating the load path. So for an example structure, loads need to be transferred from the deck to the joist to the bearer, from the bearer to the column or pile, and then ultimately into the foundation. And each transfer point, the connection becomes a critical stress region. So just a photo here, the Hyatt Regency walkway collapse is a well-known reminder that connection detailing can govern structural performance. So in that case, the failure was not because of the idea of a suspended walkway was inherently impossible. The issue was that the connections and how the detail actually carried the load. So not overly relevant to the presentation, but as a reminder that the devil can be in the detail with connection designs, and an oversight can have disastrous effects. So the central idea I want to highlight in this presentation is engineering judgment. So basically, there's not going to be a one-size-fits-all connection type, and a number of things need to be considered. I mentioned crush blocks earlier, and we'll get to them shortly, but the aim is not to remove crush blocks. Crush blocks are important and necessary in the right locations. The aim is to stop using them where the connection selection framework does not justify them. If we add a crush block where it is not necessary, we add direct supply costs and installation time and complexity without a proportional structural benefit. And obviously, if we completely exclude crush blocks, then we risk crushing, pull-out, delamination, fatigue, or poor long-term performance. So optimization sits between those two extremes, and it means matching the connection detail to the load type, orientation, and the installation methodology. So that is the mindset that will become key when we get into our case studies. Okay, before we compare connection types, we need to look at why FRP connection design is different to traditional materials. So FRP is very strong, lightweight, and corrosion resistant, but it is not isotropic, it is anisotropic, which means it does not behave the same in every direction. This becomes a key consideration for connections. So pultruded FRP has a very strong longitudinal performance because the fibres are predominantly aligned along the length of the member. So if you can imagine trying to pull apart a plaited rope, it is very strong. But transverse is different. It is not as strong due to having less fibre percentage in the transverse direction. So loads acting across the fibre direction, through the wall or around a fastener hole can create local effects that do need to be managed. FRP also has a lower shear modulus than steel, so local deformation and load transfer need to be considered carefully. And because many structural FRP profiles are thin, hollowed walled sections, such as SHS, RHS, and CHS sections, the wall of the section may need local support at fastener locations. So that's where crush blocks and crush tubes come to it. So the same external load can require a different connection depending on the fibre direction and the profile you're using. So section geometry is often the difference between a necessary crush block and an unnecessary one. So wall thickness affects local bearing and crushing resistance. So a thin wall will obviously behave differently to a thicker wall under the same load. And hollow sections can also be vulnerable to local wall deformation, particularly when a bolt is over tightened or when you introduce a load through a small contact area. And as touched on before, loads acting along the fibre direction is not the same as going across the laminate. So as counterintuitive as it might sound, using a larger profile to reduce connection complexity may end up being the better option for a project. As a rule of thumb, thin-walled hollow sections with transverse load demand tend to require crush blocks. thicker wall sections or connections dominated by longitudinal force may be able to use bushes or riveted brackets. Connection design, especially in FRP, is really about managing local failure risks. So fastener holes can create stress concentrations. That means the area around the hole can become a starting point for failure if the load is not properly distributed. So FRP can also be more vulnerable where loads act through the thickness of the laminate because that's not where the material is typically strongest, as mentioned. So, and if the load is poorly distributed, the laminate can delaminate, which means the layers of the FRP can actually pull apart rather than acting together. This would generally be at risk, similar to before when you're using thin-walled hollow sections when the load is in the transverse direction. Some other common failure modes need to be considered in FRP and probably generally in other materials as well. So bearing failure, so local damage on or around the contact point by a concentrated load. Net tension, which is when the remaining section left around a hole is not sufficient enough to carry the tensile force. Shear out occurs when the fastener tears a path towards the edge of the member. So cleavage is like a splitting type failure, and delamination is separation of the laminate layers, as mentioned, and bolt pull through occurs when the fastener or washer zone pulls through the section. The important point is that these failure modes are not random. They are influenced by load, direction, magnitude, edge distance, bolt hole sizes, bolt spacing, and wall thickness. Now that we have covered the material behavior, we can look at the three main practical options used in FRP design. So the three options are crush blocks or inserts, bushes or crush tubes, and rivets. So each has its place, and the challenge is deciding on the best option for each connection. So at a high level, crush blocks provide the highest local reinforcement for high demand bolt joints. Bushes provide a middle ground solution. They support the bolt hole and help distribute local stress and improve bolt performance where full transverse reinforcement is not required, as well as eliminating the crush of the hollow sections when the bolts are actually tightened. And riveted connections are usually in conjunction with a bracket and are permanent, efficient, very fast, and for lower demand joints, particularly where access or alignment makes bolting more difficult. The right system depends on loading, FRP properties, as mentioned earlier, and the installation method, so access, sequencing, and site limitations. So we should not think of these as good or bad options. We should think of them as different tools for different connection conditions. Crush blocks when they are required. So crush blocks are required where the connection needs the highest level of local reinforcement. So typical triggers for these are high compression, high bearing, high shear, or high pull-out loads. And they're also important where long-term bolt preload is critical to be maintained, and where the dominant stresses act transverse to the fibre orientation, as I was saying before, or when the wall buckling is at risk for a thin-walled profile. So they therefore are generally appropriate for high consequence primary structural joints where we need the most robust connection behavior. So more often than not, in those situations, the crush block is not overkill. It is the correct engineering response for the demand. Crush blocks when they may be more than needed. So the issue is not in the use of crush blocks. The issue is using them everywhere by default. So often crush blocks can be an extreme installation burden. To install a crush block or insert, the member needs to be pre-drilled in the precise bolt hole location. Then the crush block is pushed down the member and aligned with the hole. So that takes time, especially when the detail is repeated many times across a structure. It is also often not feasible when setting out a structure, as the bolt hole locations are sometimes not known until the members are actually installed, in which case it's often too late to be able to push the insets in. And they also generally allow for no tolerance at all during installation. And they also just add additional costs, supply costs through extra components, bolts, brackets, additional drilling, especially when you can potentially substitute with something like a riveted bracket. Bushers or sleeves or crush tubes, they're a practical middle ground, so they are useful where the dominant force is longitudinal or moderate, where pull-out forces are low to moderate, and where crushing demand is lower. So when compared to a bolt alone, they improve bolt torque and tightening capacities, and they help distribute the local stress around the bolt hole. So a bush is not the same as a crush tube. It does not provide the same level of transverse reinforcement. But where the demand is moderate, it can protect the laminate and improve constructability without the burden of a full internal insert. They can be drilled and installed while the member sits in the final position, and are useful when the whole position cannot be central to the member, so create more tolerance and speed for installation as opposed to crush blocks. That makes bushes particularly useful when you need the performance of a bolted connection, but also wanting practicality for install. Rivets. So rivets are the efficiency option. They suit permanent, lower demand, non-critical connections where the loads are low to moderate. They eliminate all the alignment issues that are present with bolted connections as they are drilled and installed in their final position. So similar to how a nail or screw would be used in timber with an L bracket or plate, that's basically the same principle for rivets. Rivets are obviously not going to work in a critical high shear transverse load case, but can often make up majority of the connections in a structure like a boardwalk. They're the right answer when the load case allows speed, simplicity, and permanence to become the priority. Okay, this slide is important because it challenges a common assumption that the strongest detail is always the best detail, which is not always true. So crush blocks provide the highest security for high demand joints. Bushers provide a good balance where performance and easy installation are needed, and rivets are efficient and fast. So optimized design is about enough strength, safe installation, and cost effectiveness, and the best whole of project outcome. So the question shouldn't really be what is the strongest possible connection. The better question is what is the simplest connection that safely satisfies the engineering demand and can be easily installed. Right, part 4, selection framework. So now we will turn that thinking into a practical selection framework. So this is not a replacement for engineering design checks or capacity tables. It is a way to structure the decision so we start in the right place every time. So the first filter is load. So start by asking what are the types of loads the connection is carrying? Is it tension, shear, bearing, or crushing? Then you ask about direction. Is it load acting along the fibre or direction or across it? And then if it's along, you get both bushes. Across, you need crush blocks. And then you consider the magnitude. So if it's high pull out or high shear, high bearing demand, you usually have to go towards the crush block. And if the demand is moderate, a bush may be appropriate. And if demand is low, a riveted bracket may be sufficient. So it's just, the first decision point is just what is the connection actually doing? The second filter is actually the FRP section. So if you know the load type, direction, and magnitude, now you've got to work out which profile to use. So checking the wall thickness and like the published connection capacities for the likely FRP profiles you're thinking of using. And then ask whether the wall could potentially crush, buckle, delaminate, and then lock in some potential connection options, as there's always generally more than one connection option, even when you get to this stage. So it's key to assess each connection point individually as well. So don't assume that the one connection detail needs to fit the whole structure, because that can often lead to oversights and oversights of potential opportunities for improvement. And the third filter is installation. So a structurally sound detail still needs to be practical and safe to install. This is our last step to really lock in the connection design. So can the installer physically position, align, and complete the connection? So does the detail allow for slopes, bolt hole eccentricity, site drilling, alignment? Does it create clashes, slow assembly, or require extra handling? How often is the connection repeated across the structure? So Access, tolerance, sequencing, drilling, potential clashes can all determine the best detail, and this is where design and construction need to meet. So a bit of a decision matrix here. This is more of a starting point, not a rule book, and just summarizes what we just sort of went through. So for high pull out, high shear, start with crush block. For moderate pull out of shear, maybe consider a bush. It's worth noting that oversized washers, which we'll see in a moment, improve the pull out capacities of bush connections. So there's opportunities for improvement there. And for low pull out of shear, a riveted bracket may be appropriate. And for high bearing stress, start with a crush block. For moderate, maybe a bush. Close bolt spacing, access, installation, those things is more case by case, but it does need to be considered. Same requirement, multiple solutions. So this is where the optimization obviously becomes possible. So a connection can satisfy the same requirement more than one way. So a joisted bearer connection, for example, can be detailed with a through bolt with crush blocks or tubes, a bolted bracket, again with crush blocks or tubes, or with riveted brackets. So the best detail is the one that satisfies the capacity while improving constructability and reducing overall project costs. Okay, case studies. So now we will look at 3 case studies that show how this optimization works in practice. Each case study demonstrates the same principle. Optimization is not about reducing performance. It is about removing unnecessary complexity where the engineering review shows a simpler detail is sufficient. Okay, first case study is Jindalee Beach Stairs. So this project involved repeated pile, joist, stringer, and bearer connection, and handrail post connections as well, as you would expect from a set of stairs. So it was also a very tricky site with footings only able to be placed in certain locations in the sandstone rock. So tolerance and flexibility in the connections was a must. The original design issue was that multiple bolted bracket connections and anti-crush inserts, along with those site tolerances, created a design that was almost impossible to install without on-site modifications. So the original design was very sound and every connection was adequate. So the aim in optimization was to keep structural performance where required and maintain the good design work that had been done, but simplify the lower demand connections and using riveted brackets and through bolt details where possible. So what changed? There were 4 main changes. So firstly, the inner joisted bearer bolted bracket connections were replaced with 3mm riveted brackets. This avoided pre-drilling and pushing more than 10 anti-crush inserts per bearer. So obviously there are a lot of bearers in the structure. If they're not perpendicular to the joists due to site constraints and pile positions, then there is no way to pre-drill all the bearers beforehand. They need to be done based on joist locations, which are unknown until the bearers are actually sitting next to the piles. And once the bearers are attached to the piles, there's actually no way to push those inserts into the bearer for the joist connection because they can't push past the crush blocks that are in there for the pile connection. So second change is the outer joisted bearer bolted bracket was replaced with a heavier gusseted riveted bracket. So similar to previous, we avoid the inserts and simplify the connection, but the heavier gusseted bracket was able to overcome the loading from the handrail post. Third change was the stainless handrail offset bracket at the top of the post was changed from a through bolt just to a standard riveted offset bracket. So this avoided, again, pushing the insert in the top of the post, which was potentially creating clashes and removing tolerances in that connection. And the fourth change is the side bracket connecting the pile to the bearer was replaced with a through bolt. So this reduces the chance of a clash with the joist. It removed additional bolts and brackets from supply and just reduced the number of holes to be drilled in general. So the end result from these changes was fewer inserts, fewer brackets, less drilling, more site tolerance, and lower clash risk while still having an adequate connection type for each connection. So the supply cost reduction after the design optimization was actually passed through to the client as a discount from quoted price on this job. The second case study compares the old and new handrail post connection design from Lakeshore Boardwalk to Kangaroo Point Boardwalk. So the old approach used inserts in the outer 250 by 100 RHS joist for the connection to every handrail post. That was conservative, and it was also very time consuming to install. So design checks and testing enabled the removal of these inserts in the outer joist by using crushed tubes with an oversized square washer on the back face of the joist to increase pull-out capacity of the connection. So this is a good example of testing, turning a conservative detail into a faster, repeatable standard detail. So the installation lesson, so removing these crush blocks meant that there was no longer a need to push them into the joist for every handrail post, as mentioned. So this original detail becomes very time consuming, especially for larger spans when the crush blocks need to be pushed like 6 meters plus into the joists. And on large projects, there could be 1,000 plus handrail posts. So it can quickly become weeks or even months worth of work to actually install those inserts. Using bushes means the holes can be drilled in position to suit the handrail post after the superstructure is complete, and there's no need to position the internal crush block. So both large projects, so the install cost reduction of the handrail post to joist connection becomes very significant on this scale. Case study 3. So the third case study is the Botanica Sewer Bridge. So this is another Wagners internal design optimization. So it's focused on safer and more tolerant installation. The original issue was that inserts at the end of a bonded girder created installation challenges. So once the girder is lifted into place, the inserts could not be safely installed in the end of the girders. So the optimized detail replaced those end inserts with bush tubes. So this will allow the girders to be landed on the headstock first, then drilled in situ. So this optimization improved 3 things. First, tolerance. So in situ drilling allowed the final connection to suit the landed position. So you aren't relying on tape measurements across a 10-meter span, taken from scaffolding, measurements that need to take into account pile skew, squareness, which becomes really difficult to get accurate. And secondly, safety. So the installers will no longer have to push those inserts into the end of the girder after lifting. So potentially, which could potentially involve awkward body positioning and safety risks. And there's just constructability. So the bush tubes simplifies the installation sequence while maintaining the required connection performance. So originally, if they weren't to push those inserts in awkwardly up on the headstocks, they'd have to lift the spans onto the headstocks, mark all the bolt hole locations, bring them back down, drill all the holes and push the inserts and lift it back up and complete the bolted connections all the time, maintaining a 1 mil either side bolt tolerance for the bolt holes and having a crane on site for potentially twice as long as you need. So for this one, the key lesson is that sometimes the right connection is the one that makes safe installation possible, even if it doesn't appear to be the simplest and easiest from a design perspective. So across all 3 case studies, the same principle appears. At Jindalee, repeated brackets and inserts were simplified to reduce labour, clashes and supply costs. At Lakeshore and Kangaroo Point, the testing removed the unnecessary outer joist inserts and created a faster standard detail that can be used for future projects. And at Botanica, the bush tubes replacing the inserts improved tolerance and safety for the in-situ installation. So reducing crush blocks is not a shortcut, but is the result of engineering review, judgment, and thinking about the constructability. We will finish with simple decision logic to take back to future design. So the goal is to not make every connection lighter or remove all crush blocks. The goal is to make every connection appropriate. So if you're going to remember one slide, try and make it this one. So use a crush block or insert where there is high load, high consequence, high pull-out, high bearing, transverse demand, or preload retention. Use a bush or crush tube where there is moderate demand and the goal is to improve bolt performance, shear capacity, and laminate protection. Use a rivet or riveted brackets where loads are low to moderate, the joint is permanent and access is limited, and installation speed and efficiency matters. So in short, the simplest connection that safely satisfies the engineering demand while taking into consideration the supply and installation costs. And just some key takeaways. So connection selection to start with understanding the load type, direction, and magnitude. FRP section geometry, wall thickness, and fibre orientation directly affect connection performance. Crush blocks are required where the demand is high, transverse, high consequence, or preload critical. Bushes and rivets are sufficient and beneficial where the load requirements allow. Installation, access, tolerances, sequencing, drilling, clashes, and maintenance can determine, and often do determine, the best detail. And lastly, just spending time to optimize and make the right connection selection improves constructability, reduces installation time, and delivers cost efficiencies without compromising structural performance. All right, that brings me to the end of the presentation. I'll now hand it back over to you, Georgia, for the Q&A.
Thank you very much, Mitch and Sabin, for your presentation. We're about to dive into the Q&A session, so if you do have a question that you would like answered, pop it in the chat facility or text it to me on the mobile number in that chat. But just before we do, I wanted to tell you very quickly about our design guide and a new blog, which you are the first to see. Wagners CFT Design Guide has been developed to give engineers, designers, and project teams greater confidence when working with FRP. It brings together the technical data, design methods, and practical guidance needed to support the specification and approval of Wagners pultruded FRP structural profiles. Rather than treating FRP as an unfamiliar alternative material, the guide helps make the design process clearer and more accessible. It covers key considerations, including material properties, design basis, member design, connection design, driven piles, component design, and full structure design. Ultimately, it gives project teams a practical resource they can rely on when designing with lightweight, durable, and corrosion-resistant FRP infrastructure. Use the QR code on the screen now to read or download the design guide, or watch how to use Wagners CFT Design Guide and what to consider that's different when designing with FRP by using the QR code on the screen now. I will also include those links in today's follow-up email. I'm excited to give you a first look at our newest blog, Choosing the Right Connection, When to Use a Crush Block, Bush or Rivet. This blog looks at one of the most important parts of any FRP structure, the connections. It explains why connection detailing matters, how the right connection helps protect the load path, and why preserving the integrity of the laminate is critical to long-term performance. It also gives engineers and project teams a practical way to think about when to use a crush block, a bush, or a rivet based on load demand, section geometry, access, environment, and serviceability. The bigger message is that smarter connection choices lead to stronger outcomes. By using the reinforcement only where necessary, we can improve constructability and reduce installation time on site. So if you'd like to be one of the first to read this blog, use the QR code on the screen now, and I will also include the link in today's follow-up email. I'd now like to welcome Wagners CFT General Manager Ryan Leeson, who will be facilitating the Q&A session of today's webinar. Let's have a look at some of those questions, Ryan.
Thank you, Georgia, and well done, Sabin and Mitch. We'll pile straight into them. A question from Ahmed. Are riveted connections more efficient than sleeves as they do require a greater amount of drilling and tightening of several rivets. That's maybe for you, Mitch, that one.
Yep. Yeah, so they generally are quicker and easier to install. So you're obviously drilling a much smaller hole, and for a bolted connection and hollow section profile, you've got to make sure your bolt lines up on the other side of whatever profile you're doing. So it becomes a little bit challenging to get that alignment correct, and often drilling through with a small spade bit or tile bit can be done very quickly. So you drill through and pop rivets off almost as fast as you would be doing screws. So they do become quite fast and efficient.
Thank you, Mitch. First of two questions from Josabel. Sabin, this will be for you. Can you elaborate on the cleavage failure? What does this look like in a hollow section?
Thank you, Ryan. Thank you, Joseph, for the good questions. So usually the cleavage failure in FRP is quite brittle and catastrophic failure, which we usually try to avoid it by maintaining the resistance and indistance and more prompting the failure to the bearing failure. In FRP, the cleavage failure usually looks like the failure in the both directions, like both in the longitudinal and the transverse directions, which is usually maybe due to the forces going not only in the one direction, but in the diagonal directions. So moreover, then I feel like rather than in hollow sections, it is more like observed in the plate, FRP plate sections, where you can have the failure can be seen in the both transverse and longitudinal directions.
Thank you, Sabin. And follow on from that, which again, Sabin, you're probably well positioned to answer. Are the Wagners anti-crush inserts available for all hollow section members? The note is here in the design guide. There's no data given for the 100 by 100 and 150 by 100 RHS anti-crush insert capacities.
So yes, for Wagners hollow sections, so usually for our SHS and RHS sections, there are our anti-cross inserts. But for circular hollow sections, we usually use the tubes because they have a little bit wall thickness, and using the tubes as well, like stainless steel bush, we can get the sufficient connections. Moreover, like for example, for some of the profiles like 150 by 100 RHS sections, we still have the anti-cross inserts, but the hole size might be limited. So it's worthwhile checking with Wagners us before proceeding with the design using the particular bolt size on that sections.
And that's why we don't publish it as readily as we do for, say, the 100 by 100 or 125 or 250, is because we don't have the same spread of bolt sizes available. Is that correct, Mitch? Do you want to elaborate on that at all?
Yeah. So we don't have an endless amount of hole sizes available for the inserts for every profile. So yeah, it's worth checking with this if you plan on using an insert or a bolt size that isn't in the design guide, because we may not have that particular size available.
Okay, the next one is from Andreas, and Mitch, maybe you can start and then throw across to Sabin. Nutserts, which has caused us issues or lots of challenges, I'll call it, on a wave rider ride on Dreamworld recently. It was a underflooring system. Mitch, do you maybe just want to give a little bit of context or background on that project, and then maybe throw the technical side to Sabin as to where and when we can't use them?
Yeah, great question. We've done our time with the rib nuts or the nutserts for sure. So they, in theory, seem to be a very good solution, and we did design them into and installed on a fair number of projects. We just had lots of issues with the insulation and longevity, mainly. Well, they have to be 316 stainless steel usually to go hand in hand with our structural members. So 316 stainless steel in a rib nut or nutsert is sort of troublesome because the galling of the threads happens a lot, and once it starts to happen, or it happens when you're installing it, there's no real turning back. You have to sort of start, pulling that nutsert out of the profile, which is not an easy job, and it requires special tooling to install them as well. So we found that they were good in theory and not so good in practice. Not sure if you want to elaborate on that at all, Sabin.
Yeah, as you mentioned, except that constructional challenge, like those rib nuts and knot inserts provide excellent, especially the pull-out capacity, and just have to be a little bit careful because since FRP is a thin wall hollow section, those thin walls If it is like a longer wall, the pullout may be affected due to the flexure, like because of the depth of the wall and the thin wall. So otherwise, if like I feel like structural is good, but just all those structural constructional challenges will be there.
I think the also sourcing of riv nuts or riv squares with a long enough throat for some of the bigger profiles has also been a challenge. But again, our team are broadly across it. So if there's a specific project question or something you want to consider, it is always an option and things we have done before. Probably for you, Mitch, in a truss frame bridge like the photo on the design guide cover, what connection tool do they use between the top chord and the vertical/diagonal struts? And maybe that photo is an old connection detail, so maybe you can talk to new and old in that space as well.
Yeah, okay. I think it's just a standard sort of truss scenario with the bonded members bolted together, forming a truss. So each of those bolt hole locations would be an anti-crush insert pre-installed. In the case of those truss structures, we do all the pre-drilling and positioning of those inserts in the factory. So then for installation, it's more just bolting it together like a Meccano set, as opposed to drilling and pushing inserts on site. But it's just there's two chords, they sandwich the verticals and webs, and then the bolts go straight through all three members.
Okay, thank you, Mitch. Sabin, what is the difference between a standard crush block and glued crush block, and maybe just some of the benefits around each one? I know Mitch spoke to it in a bit of detail, but maybe if you can just elaborate on that a little bit for us.
Yeah, material-wise, like both our standard cross block and the glued cross block use the same material as a cross block material. It's just like in our standard cross block, so it is unglued, where we just push the inserts to the particular hole locations, and the load is being basically transferred through the like a snug fit and the bearing of the wall. But while in the glued inserts, like the load is being transferred through the like glue connections between the anti-cross inserts and FRP wall, as well as the bearing on the wall, which provide like a higher shear strength to our connections. And also like thinking from installation or construction point of view, like usually the glued connections are the ones that require the control environment, because we have to apply the glue and that should be cured at proper environment. So usually they are the one that's done on our site rather than on the factory. Otherwise, like, yeah, structurally the glued connections is like have the higher shear strength compared to the unglued or our standard anti-cross inserts.
Okay, thank you, Sabin. And another one for you, Sabin. One of the notes was that FRP fibre orientation is important in the design process, as obviously it governs connection capacity in different directions. Does that mean that Wagner's connection details or the underlying structural components of a Wagner's connection detail would be different to other pultrusion connection details, and it can't be easily substituted?
Yes, that's a very good question, Ryan. Yes, so every FRP are like unique, like whatever the Wagners produce are also the unique, because it produced with the different pultrusion method, having the fiber like a fiber directions both in longitudinal and transverse direction as per our design requirements. So and that's what is influencing the properties in the both directions, in the longitudinal and the transverse directions. Usually for FRP, like in the longitudinal directions, the strength is higher because more fibers are oriented in that directions compared to in the transverse directions. And also found some of the FRPs, like not our FRPs, some in the often market found the FRPs that don't have much of the transverse direction. They just use some matte fibers or those kind of things, which don't provide enough strength, like which usually don't provide enough strength in the transverse directions. So that's what will make the difference. So that's why we have to be very careful, like looking at the properties of any FRPs in the longitudinal and transverse directions in the both directions, because in reality the load in the FRP can be in like any directions. Yeah.
Understood. Thank you, Sabin. Mitch, over to you. Where do you usually see the biggest gap between what looks efficient in design and what is practical to install on site? Where do we often find contractors coming unstuck?
I would say making all connection types the same would appear to be a efficient way to do a design, and does have efficiencies in procurement and installation. But if that connection detail is one that isn't easy to install, then all of a sudden it becomes a huge installation burden. So a bit of a gap there is maybe considering the same connection type for all seems like a good option, but in reality it may not be the case, if that sort of answers it.
Yeah, and what about construction variability? What part of the construction process is where most of the variability is introduced and therefore needs to have the flexibility in the design, and what components are more fixed and therefore can be more prefabricated?
Yeah, so the piles or board pier or post positions, if they change, then your connections for your bearer, obviously pile to bearer, will change relative to the bearer itself, and then the joists on top of that bearer, the connection positioning will also change. So that's sometimes misunderstood as a on a detail. It appears that everything is square and will fit together, but if those posts or columns aren't in the correct position or exact position, then you need to modify things on site to suit. So that's probably the main oversight, I guess, when considering installation design of a sort of boardwalk, is that pile to bearer connection and the pile locations potentially changing and needing to have tolerance in your design and installation methodology to accommodate that.
I'm not sure how many people have been on site with a piling contractor before, but they don't typically work to millimetre accuracy, so you sort of get what you're given. Last question here, Sabin, and I know this is quite a big question, so give us the short answer. How do you design connections for ramps or changes in grade on boardwalks or walkways specifically?
So yeah, so design for the connection of the RAM is also like follows the typical connections we do for the joist and the bearer, but using when the connection demands the use of anti-cross inserts, we have to understand our anti-cross inserts has got just the central hole. So that means if we design the ramp with just a central hole, that means our bracket, whatever bracket gonna line up with that hole, will have to be the different custom bracket. Like there will be the various custom brackets on that bracket, so which might be tedious on site, like to match all of them once. So it's usually better to go with the ramps and kind of things, use the boost connections, where that will provide the flexibility for drilling and inserting the hole on the sides to suit the same bracket for the overall project.
Okay, well, that looks like it is our last question, so we will wrap up our Q&A session there. A big thank you to Mitch and participation in today's webinar, and also thank you to Ryan for facilitating the Q&A session. If you'd like to share your thoughts on today's webinar, please feel free to complete the feedback form by using the QR code on the screen now, and I will also pop that link in the chat. Or perhaps you'd like to be a guest speaker. If that's the case, fill out the feedback form and let me know. You could also reach out to me on LinkedIn, send me an email, give me a call. However you want to contact me, I would love to hear from you. Coming up in June, we'll be discovering how Wagners CFT are designing infrastructure for faster and cheaper construction phases, and how to translate those designs into a better bottom line for your business, with guest speakers Wagners CFT Business Development Manager Robbie Wesley and Site Manager Ben Brooks-Fevers. So if you're interested in this webinar, use the QR code on the screen now to register for your free online seat or to receive a recorded copy of the webinar. The link is also in the chat, and I'll include it in the follow-up email today as well. And once again, you are the first to hear that part 3 of this series is officially locked in. We're currently planning a July webinar, The Right Connection, using the Wagners CFT Drafting Guide. So keep an eye out for more details, and we'll also send you a personal invitation as soon as registrations go live on the website. That concludes our webinar for today. Thanks very much for coming, and we're going to go out on the video from the beginning of the webinar. Enjoy, and we look forward to seeing you next time.